In this unit, you've done some assignments that focused on rational numbers and irrational numbers. For example, you looked at the decimal representations of each of those sets of numbers. In this video, what we're going to do is just look a little bit more closely at the size or the cardinality of the set of rational numbers, as well as the set of natural numbers and integers, and the set of real numbers. A lot of students, and really the public in general, are much more familiar with integers and with rational numbers, and if you look around in the world, you'll see a lot more integers and rational numbers than irrational numbers, but what we'll see is that actually there are many, many more irrational numbers than there are rational numbers. One of the things that you've done in this unit is to find a rational number between two given numbers, and to also find an irrational number between two given numbers. And because you can always find a rational number between any two real numbers, we can call the set of rational numbers a dense set. And the irrational numbers are also dense, and the real numbers are also dense. The natural numbers and the integers, on the other hand, are not dense. So because of this, you can kind of have some intuition, and a lot of people have this intuition, that the set of rational numbers has many more elements than the set of natural numbers. And yeah, people will realize both of those sets have infinitely many elements, but come on. The rational numbers has just a lot more elements in that set. It's dense, for crying out loud. But in fact, as we'll see, the natural numbers and the integers have the same number of elements, but both of them also have the same number of elements as the rational numbers. It's not that the rational numbers is a larger set, they're actually the same size as the natural numbers. So I just said that the set of natural numbers and the set of integers are the same size, or more technically, they have the same cardinality. I also said that the natural numbers and the integers have the same cardinality as the rational numbers, even though the rational numbers are dense. In order to really think about these claims in a precise way, we need to know what we mean by same cardinality. So luckily, the mathematician Cantor gave us a really groundbreaking way to think about this. He said that two sets have the same cardinality if there exists a relation such that each element of one set corresponds to one and only one element of the other set. So now what we need to do is think about whether we can find a one-to-one correspondence between the natural numbers and the integers, and also between either of them and the rational numbers. I should say too that one of the really important things about Cantor's definition of cardinality is that it makes sense for finite sets. You could say two finite sets are the same size or the same cardinality if they have the same number of elements, because you can match them up one to one. But his definition isn't limited to finite sets. His definition actually also applies to infinite sets, because you can define a one-to-one relation on infinite sets. So let's take a look at the set of natural numbers, or more technically the non-negative integers, and then let's take a look at the set of integers. And intuition might say that the set of integers is like twice as big or has twice as many elements as the set of natural numbers. But remember, we want to think about this using our definition of the same cardinality. So we want to look for a one-to-one correspondence between these two sets. And the key here is to realize that although the integers are ordered, we don't need to put them in that order when we're looking at them in the set. The set of integers, we can move them around as long as we just keep all the integers in that set. So let's rearrange the integers a little bit, and now it becomes fairly clear to see that we can build a one-to-one correspondence between the natural numbers and the integers. So if you take a look, wrap your head around this correspondence, it shows that these two sets have the same cardinality. And you can also show that the natural numbers have the same cardinality as the even numbers. So again, people might think that there are half as many even numbers as there are natural numbers, but actually there are the same number, or that they have the same cardinality as a set, as an infinite set. The set of square numbers has the same cardinality, the set of prime numbers has the same cardinality. Anything that you can line up in a one-to-one correspondence with the natural numbers has the same cardinality as the natural numbers, and we would call that a countably infinite set. Now let's move on to the rational numbers, which again are a dense set and seem intuitively much larger than the natural numbers. We've got the natural numbers and the integers in the set of rational numbers, but we've also got a lot of other rational numbers. But what we need to do is break away from this mentality of thinking that we have to put the rational numbers in order as they are on the number line. Instead, let's reorganize them in a way that's going to allow us to count them. Because if we can count them, then we have basically put them into a one-to-one correspondence with the counting numbers or the natural numbers. So what we're going to do is we're going to lay out a grid of rational numbers. What we're going to do across the top is we're going to go through the integers, 1, -1, 2, -2, 3, and so on. And then what we're going to do down is we're going to use the unit fractions, or what we're going to do is increase the denominator. So we'll have 1, 1/2, 1/3, 1/4, 1/5. Then inside we'll form the fractions that are made by the top row and the left column. So you can see those here. Now you can check quickly that all of the rational numbers are going to show up in this grid. So we've got all of them covered, but we can't go and count everything here because we will be doing lots of double counting. So we wouldn't have a true one-to-one correspondence because we'd have some double counting. So what we need to do is we need to snake our way through the grid, and this is how we're going to count the fractions, count the rational numbers, but we're just going to skip over any rational number that is expressed as a fraction that's already been counted. So we're going to start counting with 0, then 1, then 1/2, -1, over to 2, then diagonally down to -1/2, 1/3, 1/4. Notice how we're kind of going to snake through and hit everything in this kind of snake pattern. -1/3. Then we seem like we're going to get to 2/2, but we've already counted 1. So you just skip over 2/2 and go to -2. Then to 3, skip over the -2/2 because we've already counted -1. Then continue on to 2/3 and so forth. So we're doing the snake pattern. That's a well-defined pattern, way to weave through the array. And then we're going to skip over anything that has already been counted in an equivalent form of its fraction. So in this way, we're going to hit everything. We're going to hit everything exactly once, and we are putting all of the rational numbers into correspondence with the natural numbers. Therefore, by our definition, those two sets have the same cardinality. So that is somewhat surprising that the natural numbers have the same cardinality as a dense set like the rational numbers. So at this point, people might be thinking, oh, is just every infinite set have the same cardinality as the natural numbers? Maybe there's just kind of this one size of infinity. But that's not true. If we go to the real numbers, what we find is that the real numbers really do have many more elements than the natural numbers. And what I mean by that is they have a larger cardinality than the natural numbers. So how could we prove that the real numbers have a larger cardinality than the natural numbers? Well, we would have to prove that there is no one-to-one correspondence that exists. So how do you prove that something doesn't exist? Well, the easiest way is to assume that it did exist and then find some sort of contradiction. So what we're going to do is we're going to actually narrow things in a little bit and just deal with the real numbers from 0 to 1. The real numbers from 0 to 1 actually have the same cardinality as the real numbers, and you can see it by this picture right here. There's a one-to-one correspondence between the interval from 0 to 1 and the full real number line. So we'll just work with that interval from 0 to 1, but assume that there was a one-to-one correspondence between the natural numbers and the real numbers that are between 0 and 1. With this purported one-to-one correspondence in hand, let's now consider the real number b with the decimal expansion b1, b2, b3, b4, and so on. What we're going to do is choose b1 to be a digit that's different than the first decimal place of x1, and then let's also make sure it's not 0 or 9. Then for b2, the 100th digit, let's make it to be different than the second decimal place of x2, and also let's make sure we don't have 0 or 9. And then b3, the third decimal place, let's just make it be different than the third decimal place of x3 and not 0 or 9. And then continue on so that bn, the nth decimal place of b, is different than the nth decimal place of x sub n, and then not equal to 0 or 9. Now we can think carefully about the b that we've constructed. Here's an example of a b that was constructed based on the purported one-to-one correspondence on the previous slide. There were different choices for b that you could make, but the important thing is that no matter what one-to-one correspondence you start with, you are able to build a b that satisfies those criteria that we mentioned. Now, thinking about the b, we know a few things. First of all, we know that b is a real number because it's represented by this infinite decimal. We also know that it's between 0 and 1. And it's not going to be a repeating 0 or a repeating 9, so that's going to just make things work out nicely where we don't have to worry about like a repeating 9 being equal to 1, or we don't have to worry about even like a 0.499999 repeating, which is actually equal to 0.5. We don't have any tricky stuff like a decimal trying to hide and dress up in different clothing. So we have b, it's a real number between 0 and 1, which means it must be in the right column of our one-to-one correspondence. But we also know that B is not in the right column of our one-to-one correspondence, because we know that B is different than x sub I for every single I, because B and x sub I are different in the ith decimal place. So if they have one decimal place that's different, we know that those are different numbers. So B is in the right side of the one-to-one correspondence, but B also is definitely not in the right side of that one-to-one correspondence. That's our contradiction, which means that the one-to-one correspondence actually did not really cover all the real numbers between 0 and 1. And actually, no matter what one-to-one correspondence you think you have, you can always construct this B, which means you never actually get a full one-to-one correspondence to the real numbers between 0 and 1. That proof by contradiction can be attributed to Cantor. It's usually referred to as Cantor's diagonalization process. And what does it really mean? Well, at the end of the day, what it means is that the interval from 0 to 1 has a larger cardinality than the natural numbers, and really then means that the real numbers have a larger cardinality than the natural numbers. The real numbers have a larger cardinality than the evens, than the integers, than the rational numbers, and so on. We've found a sort of a bigger infinity, so to speak, a larger cardinality, and that is called usually the continuum. So the continuum is a larger cardinality than a set that's countably infinite. So where are all these extra numbers coming from that make the real numbers so much bigger than the rational numbers? Well, it must be the irrational numbers. The irrational numbers must be a pretty serious player that are thrown in there and make the real numbers just that much bigger than the rational numbers. So that gives us this intuition that the irrational numbers is actually a much larger set, so to speak, larger cardinality than the rational numbers. Even though people are much more familiar with rational numbers and you see them much more often, the rational numbers are actually just a drop in the bucket compared to the ocean of irrational numbers. Another way to think about the fact that the set of irrational numbers is just a much larger set than the set of rational numbers, irrational numbers has a larger cardinality than the rational numbers, is to think probabilistically about building up a number. And we're going to think in terms of the decimal representation of the number. So what we're going to do is we're going to think about building just some real number, and then we'll ask ourselves, is that an irrational number or a rational number? And see probabilistically which one is more likely. So what we're going to do to build our real number is we're going to just start throwing digits down. And let's just work, from numbers between 0 and 1 again, because that's equivalent, in terms of cardinality to the real numbers. So let's take 0 point, and now let's start randomly generating digits. So 0.471128, and so on. And just think about these digits as being thrown on there by a random digit generator. Now this random digit generator, it could generate any of the real numbers. But now let's think about if we're going to get an irrational number or a rational number. To get an irrational number, we would need these random digits to be coming, and we would need to make sure that there's never a repeating pattern. To get a rational number, we would need to make sure that we do get a repeating pattern, either like zeros repeating all the way on to the right after some point, or some pattern like 0.14141414, where that 14 repeats on and on. You guys already showed that if you have this repeating pattern in the decimal expansion, it corresponds to a rational number. Now think about that random digit generator, and now think about the likelihood of getting a non-repeating pattern, which would be an irrational number, and the likelihood of getting a repeating pattern, which would be a rational number. That random digit generator might hold up for a pattern for a while, and it might even hold up a pattern for a long while, but you've got infinite decimal places to fill. And so there's a 0% chance that your random digit generator is going to continue the pattern on to infinity through all the decimal places. At some point, that random digit generator is going to mess up the pattern, and as soon as you mess up the pattern, it's not repeating anymore, which means you ended up with an irrational number instead of a rational number. So this actually leads to a probabilistic conclusion that if you randomly generate a real number, you have a 100% chance that that's going to be an irrational number, and a 0% chance that it's going to be a rational number. So that's what I meant by saying that there's this sea of irrational numbers. Anywhere you dive in is going to be an irrational number. And the rational numbers are actually these very special things that exist, but if you just randomly pick a number, it's not going to be a rational one. That's how scarce they are. But
they're still dense.